I'll talk about a recent hobby of mine. Yeah, so on and off, I think about these Rydberg atoms and Ponderomotive optical lattices. And over the last couple of months, I did some new stuff on it, and that's what I mostly will talk about. So the talk is about Rydberg atoms and Ponderomotive optical lattice. I'll first explain what that is all about. Just that I don't forget this at the end. So here I'm listing the graduate students working on this project. That's mostly Kelly Young and Sarah Anderson. And if I have time towards the end of the talk, so after I've gone through results on Ponderomotive optical lattices, I might show some little older results on trapping of Rydberg atoms in inhomogeneous magnetic fields. And more recently, we did some trapping in a transverse magnetic atom guide. Okay, so the Ponderomotive effect can be most easily seen in a simple classical calculation. So you just assume an electron starting at rest, you turn your laser field on, then you write down the position and the velocity and the acceleration as a function of time. And then in order to get the Ponderomotive energy shift, you just integrate the kinetic energy of the electron over one cycle and take the average. And this is what you come out with. That's the well-known expression for the Ponderomotive energy shift. It's proportional to the intensity of the laser field, and it's proportional to 1 over omega square. There's been in the past a lot of evidence for these Ponderomotive shifts. So just to remind you, so in 80s and 90s, there were a lot of experiments using on above threshold ionization and multi-photon ionization. And in these experiments, there was very clear evidence for the reality of this Ponderomotive shift in that it changes the velocity of electrons in time-of-flight experiments coming out of these ionization events. Also, if you do multi-photon ionization, you can see in certain settings that as the laser pulse turns on, the Ponderomotive shift might tune a Rydberg resonance through a Rydberg state through a resonance, and you would see a corresponding enhancement of the multi-photon ionization rate. So all these things have been seen in the past. What we are interested here today in is looking at the Ponderomotive shift effects at considerably lower densities and in settings of an optical lattice. So we consider two laser beams counterpropagating. It's just a one-dimensional optical lattice. We write down the electric field as a function of position and time. Now, an important statement is that if you look at the range of this quiver motion of the electron, that at our intensities comes out at about just a couple of picometers. So the extent of the quiver motion is really tiny. That's important because if you have a case where the range of the quiver motion is much shorter than the length scale over which the electric field is changing, then you can basically locally calculate the Ponderomotive shift and assume that the electron energy is just locally shifted by that amount. And you get a force effect on the average coordinate of the electron. So basically what they are doing is a type of Born-Oppenheimer approximation. In our case, this is very well satisfied because the period of the optical lattice is in the range of 1 micron, whereas, as I said, the quiver energy amplitude is just in the range of picometers. So we can, in order to get the effect of the standing wave light field on the electron, we just write down this expression as a function of position. And this is what you get by doing that. The depth of the Ponderomotive optical lattice, you refer to this as Ponderomotive optical lattice. The depth of this lattice is given by E square times the amplitude of the field square of a single beam divided by the electron mass omega square. So if you do experiments on actually free electrons, that has been done recently. Actually, there's been several experiments. The first one in that regard was an experiment by Phil Buxbaum. They scattered electrons, free electrons, in high-intensity laser pulses and saw evidence of the Kapitsa-Dirac scattering. And then more recently, there was an experiment where some where researchers at Nebraska, they basically sent an electron beam through a standing wave light field and could directly see the Kapitsa-Dirac scattering. So if we now move on to Rydberg atoms, if you think about Rydberg atoms, there are several timescales involved. So one timescale I already mentioned, if you put the Rydberg atom in a high-intensity light field, you'll still have this quiver motion of the electron. That happens at a frequency of the order of 10 to the 14 hertz. Then, so since the Rydberg wave function is very extended and the internal timescales of the Rydberg atom are quite long, you get a significantly slower motion that typically happens at the Kepler frequency. Okay, so the intermediate timescales of the problem are the Kepler frequency and any precession frequencies you might get if the Rydberg atom is also inserted into external electric and magnetic fields. Now you notice that between this timescale and this timescale there's a couple of orders of magnitude difference. Therefore, you can do a Born-Oppenheimer separation of the motion in the rho coordinate, it's the quiver coordinate, and the internal coordinate of the Rydberg atom. Then finally, so in order to do a full job, since we are talking about cold atoms, the center of mass coordinate is also of interest. If you make estimates of the center of mass timescale, you can find that it's a couple of orders of magnitude slower than the internal coordinate of the Rydberg atom. So if needed, you can do another Born-Oppenheimer approximation at this cut. Okay, so in this talk I'll show results on the adiabatic potentials and the adiabatic wave functions of Rydberg atoms in a Ponderomotive optical lattice. So what are these good for? Yeah, so can look at a review article about atoms in optical lattices. So this topic with Rydberg atoms in optical lattices is quite related, obviously. So we use the adiabatic potentials usually if you can use a classical model for the center of mass motion of the atom, but for the internal dynamics we use a quantum model. So it's a semi-classical concept. So the idea is that you basically hold on to your atom and imagine that you gradually drag it through the optical lattice. So you have classical control over the center of mass coordinate, but as you drag the atom through the optical lattice, you allow enough time that the internal degree of freedom of the Rydberg atom can adjust to the local conditions, so local conditions of the atom field coupling. Also, what we can do and what we get out of this is, so when we get the adiabatic potentials, you can basically look at them in a way similar to molecular potentials in a molecule. So you can calculate they play a role of Born-Oppenheimer potentials. If you're interested in the center of mass motion, you can use these potentials basically as just a classical potential for your center of mass dynamics. What you can also get out of these calculations is whether, so how much mixing occurs. We'll see that this is very important in this particular problem. You can also estimate, so if you look at the adiabatic potentials, just like in molecular physics, if you look at the size of the anti-crossings, you can tell how much non-adiabatic effects will be important or not. Okay, so this is our Hamiltonian. There's a core potential. We take care of the fine structure coupling. A important point is, it's just following the concept I explained. There is, I'm sorry, so I think these are a little bit hard to see, so but there's a C and a C naught. The C is an internal coordinate, and the C naught is the center of mass coordinate of the atom. The C naught is just a fixed parameter of the Hamiltonian, so we vary the C naught. The C naught as a parameter of the calculation, and all other things except the C naught are operators. In the following, so we'll just expand that. So you can expand the potential as a sum over polynomials with coefficients you can look up, and then rewrite the Hamiltonian in the usual spherical basis. So if you look at that, so what's in there, so there's the unshifted energies. And so here we have radial matrix elements. So we see that the radial matrix elements go in principle up to infinite order. That's because if you expand the Ponderomotive optical potential, so since it's a sine wave essentially, its expansion is an infinite sum of polynomials. And similar for this angular matrix element. So note that there's a cosine to the p there. P is the same order as in there, and the c's are just Clebsch-Gordon coefficients. Okay, so then you can rewrite the angular matrix elements a little bit. So note that I didn't say that. So we have a one-dimensional optical lattice, and optically, and so we'll use the direction of the laser beams as our quantization axis. So the M quantum number is defined relative to that quantization axis. Okay, so we can re-express the angular matrix elements and insert that back into the Hamiltonian on the previous slide. And so we get the Hamiltonian that we eventually put in a computer. So at this point, it's basically just busy work. So you have to get your radial matrix elements and make sure that you don't mess up any of these many things. Okay, so here's a result that we get for a Ponderomotive optical lattice that's about 2 gigahertz deep. That corresponds to about, to give you an idea, to focusing about 100 watts of YAG laser power onto a spot that's about 20 or 30 micrometer across. Okay, I also want to say, I already said that, so we do all these calculations for 1064 nanometer wavelengths, obviously, because that's the YAG laser wavelengths. And we also do it for rubidium, so all the levels that you see use the published quantum defects for rubidium. So you see that if you do the calculation for relatively low-lying state, n equals 30, we get potentials that look pretty much all the same. And that is readily explainable by the fact that if you have a kind of a tiny Rydberg atom and you ask the question, what's the Ponderomotive shift of this electron, of the electron in the Rydberg atom in the laser field, since the electron is the Rydberg atom is much smaller than the periodicity of the lattice, mostly what you get is just the local shift, the local Ponderomotive shift. So to lowest order, you'd expect this to be the Ponderomotive shift for all the levels. So that explains why they mostly fall on this sinusoidal curve. If you look a little bit closer, so we see that there's a couple of separated levels that sort of fall out of the sequence. These are the low angular momentum levels that are separated by the quantum defects. And so since these are quite far away in energy space, these low angular momentum levels actually don't mix with all these high angular momentum levels. This incidentally, so these are just the G states of rubidium. Then if we look a little bit closer in what these high angular momentum states are doing, there's some regularity in that. So you see that there's regions in which the quantum levels roughly fall on parallel lines. That's like there and there. And then there's these cusp regions where the structure is slightly different. And we'll explain as we go where these structures come from. If you go to higher quantum numbers, like here we go to n equals 45, the qualitative behavior is still the same. It's just that the region of space of the region where the energy levels are following parallel lines, the relative importance of these regions becomes less, whereas the relative importance of these cusp regions increases. Okay, it turns out that in these linear regions you can model the effect of the Ponderomotive optical lattice on the Rydberg atom using a effective electric field model. It's relatively simple. Okay, so you look at the Ponderomotive lattice. It produces a Ponderomotive potential that has linear regions. In these linear regions, you can say basically that that potential equals the effect of a homogeneous electric field plus a constant. So if you adopt this model, then you can immediately see, if you look at the Ponderomotive potential, that the maximum electric field at the inflection points of the lattice should be given by this expression. So the potential depth times the K number divided by the electron charge. And with that knowledge, you can predict what the energy level spacing should be between adjacent adiabatic potentials near the inflection points of the optical lattice. So what I do here is I plot the results for these energy separations obtained in the simulations as a function of the principal quantum number. And so we see that for small angular momentum, mj equals 2.5, the observed energy spacing sort of tracks up to about 35, that expectation. If we go to much higher angular momentum, m equals n minus 2.5, so these are almost circular states, we see that that simple expectation is valid over a much wider n range. That can also be readily understood. So what basically makes the difference between this effective electric field model being valid and not being valid is just the relative size between the Rydberg atom and the optical lattice. The Rydberg atom, if you consider a low angular momentum Rydberg atom, its wave function is roughly symmetric, so its diameter is about 4n squared in atomic units. I can write down an equation that this size has to be much less than a quarter of the wavelength of the laser. That's half the size of a lattice well. Then you come out with an expectation that for small angular momentum, the effective electric field model should be valid for n less than about 35, and that's indeed what it does. You can do a similar consideration for circular states and come out that for circular states we expect validity of the effective electric field model up to about n equals 180. So basically what you see is, if you look at a circular state wave function, this is your quantization axis. The wave function is sort of compressed in a plane transverse to C. And that makes the effective electric field model valid over a wider range of n. This is just to make that point once more. Here I compare the adiabatic potentials for n equals quantum number n equals 65 for a low angular momentum case. We'll talk about that a little more later. And the higher angular momentum case. So this is a mess because the atomic wave function sort of skips over in neighboring wells, and that complicates the adiabatic potentials. If we crank up the angular momentum, the structure becomes more regular because the wave function becomes more localized in the xy plane. Near the maxima and minima of the optical potential, we can use an effective magnetic field model. That comes out of an expansion of the Ponderomotive optical lattice potential near the maximum, for instance. Now, the most important thing to see here is that we see a term that looks very similar to the diamagnetic term. The diamagnetic term is given by this expression, 1/8 b square rho square. Rho square is r squared times sine theta square. So you see an analogy between this term and this term. If you work it out, we expect that near the maximum of the Ponderomotive optical lattice, the spectrum should look very similar to a diamagnetic spectrum with a effective magnetic field given by this expression. So E0 is the electric field of one laser beam alone, and C just the velocity of light. And so there's been a lot of research in the past on the diamagnetic problem. I'm just giving a couple of references there. And so what one of the findings is, if you have a magnetic field that puts you well into the L-mixing regime, the energy level spectrum is adjacent sequences of rotary and vibrational energy levels. And that's actually what we see in the adiabatic potentials of our Ponderomotive optical lattice problem. If you look at the maximum of the optical lattice, you see a set of quantum levels at the bottom end of the spectrum that have equal energy separations. So these are the vibrator states. And the rotator states have energy separations that increase with quantum number. These are found on the top end of the spectrum. And so that's basically just the adiabatic energy levels taken at the maximum of the Ponderomotive Optical Lattice potential. You can also look at the adiabatic wave functions. This is just a blow up of some simpler calculation near the maximum of the Ponderomotive Lattice potential. Here we neglect fine structure and so forth. And I show wave functions for these three conditions. So this is a vibrator state, rotator state, and something in the middle. And so we see that the vibrator state is this one at the bottom end of the spectrum. This is a state that's basically elongated along the axis of the optical lattice. And it's just like in the diamagnetic problem, that's the fundamental vibrator state. And at the top end of the spectrum, you find the fundamental rotator state, which is a state where the electron wave function is basically spread out the most possible way in the xy plane. In a magnetic problem, you would say the electron wave function would be spread out the most in the plane transverse to the magnetic field. And so this obviously is a state in the middle somewhere. And how much more time do I have?
5 more minutes.
Okay. So there's also transitional cases. So if you deviate from a maximum of the optical potential, you can model the situation by parallel and electric and magnetic fields. And so that also has been looked at in the past. So I want to point out, so if you look at, so I'll just show this. So this is a paper from 1993 on an experiment of helium atoms in parallel electric and magnetic fields. If you look at the spectrum they obtain, it's in the background there, and the spectrum that we get for a Rydberg atom in a Ponderomotive optical lattice, that they look very similar to each other. So you can basically find a lot of analogy between the Ponderomotive optical lattice problem and Rydberg atoms in parallel electric and magnetic fields. We can also, in the computations, calculate the spectra. And so in this example here, I have a Ponderomotive optical lattice. The z-axis is now pointing along the vertical. And I have added a homogeneous electric field in the background, with the homogeneous electric field being parallel to the laser beams. That distorts the lattice potentials a little bit. And so you can calculate sample spectra. So here I was assuming that we do excitation out of the rubidium 5p level into Rydberg states. And the point to make is that these spectra are, if you look casually, they are undistinguishable from spectra people obtained in the past, looking at Rydberg atoms in parallel electric and magnetic fields. Okay, so we can also calculate wave functions, and so since I don't have too much time left, I'll just play this movie there. So this movie shows basically just one wave function after the other, and all it has to be at this point is of some entertainment value. I hope it works. Okay, you see nice sequences of rotators and vibrators. Then at some point you get a circular wave function like this one, and at the very end you get a conical wave function. So there's all types of interesting looking structures, and they all have some explanation. So just to point out what one can do, for instance, to understand these structures. In order to understand the conical wave functions, for instance, since we are in a perturbative regime, you can in lowest order assume that the electron is just shooting out at some angle relative to the optical lattice and coming back. Now, when is this trajectory stable? It's stable basically when the transverse momentum change integrated over one period of the oscillation comes out to be 0. So we can do this calculation. So we integrate over the transverse momentum change over one oscillation period, and plot that as a function of the launch angle of the electron. And you get these, this is the launch angle. This is the transverse momentum change. And you get these zero crossings. The zero crossings are obviously the points of stability. So we looked that up. So these zero crossings exactly correspond to the angles of these conical wave functions that come out of the quantum calculation. We've done some initial experiments on Rydberg atoms in Ponderomotive optical lattices. So we start with very simple things like measuring Ponderomotive optical lattice effects with states that do not mix. So what I showed in the last slide was a case of substantial mixing. So the wave functions are quite complex. But there's always these non-degenerate levels that are displaced to the bottom due to the quantum defects. These are not mixed. So here, for instance, I show the Ponderomotive shifts for S-state wave functions as a function of atom position in the lattice and as a function of principal quantum number. Because of the size of the Rydberg atom, which changes from one quantum state to the next, the Ponderomotive shift will change a little bit from n to n. So if we take a microwave spectrum where we excite from one S level to the next S level, so this would be a 2-photon microwave spectrum, we expect to see frequency shifts. And you can calculate these frequency shifts as a function of principal quantum number of the state you are starting in. So here I plot the principal quantum number of the initial state in the Rydberg, in the microwave transition. And on the y-axis, I plot the frequency shift that we expect. Now only look at the black stuff here, ignore the red dots. So the black line shows the frequency shift for an ns to n+1 s transition. And so we see that it takes a certain value. It becomes maximal around n equals 50. So our experiment that we are doing right now is measuring this frequency shift for a transition from about 50 to one state up. And so this is how some of the experimental details look like. So we have counter-propagating laser beams to make the Ponderomotive optical lattice. We have the canonical blue and red excitation beams for these experiments. This graph here just shows that the microwave spectroscopy works. So we do an S-to-S transition. The line width is about 10 kilohertz. This shows a Rabi flop data. It demonstrates the fact that the microwave spectroscopy works. And this is the timing of the experiment. We have an excitation pulse where we make Rydberg atoms. These are immersed in the microwave field plus the optical lattice. And at the end of the interaction time with the microwave field, we do state selective field ionization. And so the first thing to do is make sure that the lattice is aligned right. This is done actually using optical spectroscopy. So the lattice light produces a red shift for the 5s state, a blue shift for the Rydberg state. And so we have a fixed lower transition frequency, and we vary the upper transition frequency. And get spectra like that. So there's always two signals as we vary the blue frequency. So there's a signal from atoms outside the optical lattice that gives a frequency marker, and then some structure off to the right that basically tells us what the depth of the lattice is. And so we can send only one beam in, and then we get basically a spectrum that reflects the profile of the dipole trap. If you allow the retro-reflected beam coming in, then we actually make an optical lattice, and the frequency shift becomes much larger. So that's the red line. So this is how we initialize the experimental setup. And then, so we do this microwave spectroscopy experiment. We have relatively short interaction times because we want to make sure that the atomic motion plays as little role as possible. So here we use a 3 microsecond interaction time. And so this is really poor representation. So, but what we are supposed to see is, so this line there is without lattice. And this red line, this is the spectrum that we get with the lattice turned on at some intensity. And so at 1.2 watts. So we get a enhanced side peak over there. And the one that you don't see, but I can see it really well on my computer, there is another curve that's sort of peaking around there. So that's for 0.6 watts. So this side peak here is basically the shift effect due to the Ponderomotive optical lattice on this microwave transition. Okay, how much time? One or 2 minutes. Okay, so then so we also think about driving microwave transitions using modulated optical lattices. So there the idea is to, let's just explain that on this drawing here. So we generate a lattice that oscillates between a low amplitude and a high amplitude. And the modulation occurs at a frequency uppercase omega. So if this modulation frequency uppercase omega corresponds to dipole to a transition between Rydberg levels, you can drive that Rydberg transition. It's just by the fact that you apply a time-dependent potential. Now the nice thing about this method is that there's no selection rules. So that really makes this good. So if you do microwave transitions, you have selection rules, and if you want to drive high angular momentum transitions, you have to crank up the power, and so that shifts your levels around. In this method, with Ponderomotive optical lattice, so since you're not applying a linear potential but a sinusoidal potential that varies in time, there's no selection rules. And so you can go through a whole range of calculations, but the upshot is, so in this sample calculation that I did here, you basically get the same Rabi frequencies for delta L equals 0 up to delta L equals 6 transitions. This is the same lattice. Okay, so as advertised, I will probably not talk about the Rydberg atom trapping stuff, and I'll stop at this point. Thank you very much for your attention.
Thanks for that. Questions?
Yeah?
So if I'm going to design an optical lattice, I go and I calculate the light shift by calculating the polarizability of the state. And I can do that for a Rydberg state, and I find the Rydberg polarizability is about the free electron polarizability. I never say the word ponderomotive. Is this different physics, or is just another way of doing the same thing?
What you say is basically entirely correct as long as your atom is small. So if you're, that's actually, so if you look back on one of my slides here. So in this, as long as your variations in the lattice potential are kind of over length scales that are longer than the size of the atom, that's exactly what you do. So you just get the shift of you take the free electron polarizability. Basically what you have to do is when you turn the optical lattice on, you have to average that shift using the square of the wave function as a weighting factor. And that changes things. So, and what I found the most fruitful method is you just take the Ponderomotive potential, add it to the Rydberg electrons potential, and just solve the problem. So you get mixing effects, you get lots of different adiabatic potentials. But that's just like for normal optical lattices. What's different is that you have a whole lot more optical potentials, just because there's many more states. What's also different is that the size of the internal state wave function is of the order of, or sometimes even bigger than, the periodicity of the lattice. And that's all included in the calculation here that I showed, so it's an exact solution. Also, what's a difference with regard to normal optical lattices? So if you do a normal optical lattice with ground state atoms, if you get mixing effects, it's between magnetic substates. So you basically, if you look at the adiabatic states, these are spin states as a function of position. So in this case, you actually have electronic wave function that's a function of position. So that's another qualitative difference.
Question, just for the overall size of these modulations, would the optical lattice, I guess, bind just a pure electron inside the well depth, or would they be not confined in that kind of potential?
Yeah, it depends on the energy of your electron. Yeah, so it's.
Okay, but if there would be a ground state electron energy that would sit inside one of these wells. The well depth is enough to do that.
The well depth is just 2 gigahertz for a free electron. So that's not very much. So now there were experiments with high-intensity laser pulses where they actually trapped electron clouds in Ponderomotive Optical Lattice. But that's different. So this is a totally different parameter regime. So I wouldn't expect to trap any electron in there. But so if you look at the depth here, I was talking about a couple of gigahertz. That's, of course, enough to trap an atom.
Yes, yeah.
But it's not enough to trap an electron once you yank it free of the atom.
I was going to ask about trapping. So, can you see effects of then some of these states that are trapped in the lattice?
Yeah, we are looking for that. So they should be trapped. So the challenge is, how do you see that? So the Rydberg lifetime is only about 100 microseconds. Then you have thermal transitions that makes things just worse. So you have about 50 microseconds to work with. And so what you cannot do is just turn this optical lattice on and watch your atoms fall, because during 50 microseconds they wouldn't fall far enough that you can tell the difference between the trap working and not working. So you have to do something else. So you can, for instance, excite a sloshing type or a breathing type motion of your atom sample. And so there you might be better off, because the time scale for these oscillations is in the range of 10 to 100 microseconds. So that's within the time frame we can work with. So that's actually our plan, yeah, so to demonstrate the trapping effect using sort of sloshing type and breathing type wave packet motion studies.
Oh, sorry. I was wondering, you showed your excitation spectrum for these states in the first part of your talk, and when you were looking at the different the things that look like sort of like the states in the parallel electric and magnetic fields. And the question is, you know, if you're starting from a low-lying state, are there particular selection rules or symmetries so that most of the states actually turn up because of their strange shapes or are dark and don't absorb, or are they so mixed up that pretty much everything has some low angular momentum character that you end up seeing pretty much all the kinds of states?
Yeah, so it's like this, pretty much like the static fields. So so since we always have quantum defects, right? It basically takes a certain threshold field in order to mix, say, the S or D character into your hydrogenic states, and then you will start seeing them. So this is, let's see, yeah, okay. Okay, so here we are in a regime of substantial mixing. So here a lot of the D state has already been mixed into all these adiabatic potentials, so that's why they all show up. If you do the same calculation, so that's actually interesting. So if you do the calculation for hydrogen, everything scales. Okay, you get the same results if you use just proper energy access. If you do it for rubidium, nothing scales anymore. So because you have to take the quantum defects into account. So if you take this lattice and divide its steps by a factor of 10, reduce the bias electric field by a factor of 10, while this part of the diagram will still look about the same. Your spectrum will basically be gone, just because you don't have enough mixing for making these high angular momentum states excitable.
What happens if you have circular polarizations or even polarization gradients in these?
Yeah, so the Ponderomotive energy shift is not polarization dependent. So it's only the local intensity that matters. So this potential perturbation that you add to the Rydberg wave function does not depend on polarization. So it just has to be such that your polarizations are good enough that you can make an optical lattice. But you can sum over EX squared plus EY squared plus EC squared, and you don't need to have to take any cross terms.
So I didn't quite understand your excitation spectrum there. When you had one of the dipole trap beams on, you saw something shifted 30 megahertz. When you put the retroreflection on, it smears out. Now, does that mean that you're not actually trapping the atoms in the lattice?
Not all of them are trapped. That's correct. And so that's one of the reasons why we want to keep the microwave period as short as possible. So because the assumption we are working on right now is that the atoms are not trapped. So we basically excite them at the bottom of the optical lattice, and then the experiment has to happen quickly enough that during the duration of the experiment they don't move substantially.
You think if they were in the optical lattice, the red trace would also be sharp.
Right. So, but this is okay. So this is basically just showing how the atoms are distributed in the optical lattice for the ground state. So the dipole trap. In the dipole trap, you can actually see that there's quite a bit of localization at the bottom of the trap. In the optical lattice, when we turn on the retro beam, so ideally you would expect a peak at a distance that's 4 times this frequency out. So we can get to about 2.5 times that frequency out. The reason why we can't get 4 times is just because the retro beam is attenuated a couple of times because it goes through windows and such. The reason why the red curve is not bumped up to the right, like the blue one is because when we turn the optical lattice on, the atoms apparently, that's just a feature of the mod. It's just a feature of how we load the dipole trap. While with the dipole trap, the atoms settle at the bottom of the single well that the dipole trap makes. In the optical lattice, the atoms do not settle down here, so they kind of hang out halfway down.
Okay, I think there's plenty of time to talk to Georg during the coffee break. Let's thank all the speakers for this whole